Okay. So I just discuss you some idea about the spaces. Okay. You know what is a Euclidean space? Okay, so I just tell you. Suppose I have imagine that I have 2 points. Okay, in a plane, 2 points in plane. For example, this is 1 point, x, y. Okay, there is a neighboring point very near. Okay, suppose this point is x plus dx and y plus dy. Dx and dy are very small. Then what is the distance between these 2 points? This distance, the straight line distance. You will use Pythagoras theorem. Okay, because this distance is dx and this distance is dy. This is dx and this is dy. If I use Pythagoras, this distance I call it as ds. Then I can write ds square is equal to dx square plus dy square. Okay. In other words,
हेलो सर.
suppose
सर आप कुछ शेयर कर रहे हैं स्क्रीन?
you cannot see.
No sir.
I have shared it. Nobody can see it.
Sir, we can.
Sir, it's visible.
Okay, okay. Now is it visible?
No sir.
Yes, sir.
Yes or no?
Yes sir.
Sir, she
Okay.
might be having network problem.
Maybe थोड़ा network एक बार you off करके फिर करो. Okay. So now instead of this, they are near points. Suppose I have this point x1, y1 and this point is x2, y2. Then you use the distance formula. Distance between them is d. Suppose the distance between them is ds. Then how will you write? ds square is equal to x2 minus x1 whole square plus y2 minus y1 whole square. This is our distance formula. Or ds is equal to, you usually study root of this. Okay. So usually when 2 points are very near to each other, that distance between x1 and x2 can be represented by what is called dx, a small distance. Okay. So say that this is usually called the Euclidean metric. This is called the metric, Euclidean metric. Okay, so this is the usual name given to it. Okay. Now suppose you are in space. This point is x plus dx, y plus dy, and z plus dz. Okay, then the distance square, suppose ds is the distance, then I can extend this. ds square I can write dx square plus dy square plus dz square. This is a kind of extension of Pythagoras theorem from 2 dimension to 3 dimension, the distance between them. And some of the points which I want to look to bring to your attention is that ds square, when I write dx square plus dy square plus dz square, the coefficient of dx is 1, the coefficient of dy is 1, the coefficient of dz square is 1. So all the coefficients are 1. Okay, and you never find that it is it is different from 1. It is not that is not you are seeing. Now suppose, can you imagine, see, this is usually called the Euclidean metric. Okay, so this is the Euclidean metric. The distance is usually called the Euclidean metric. Okay, now can you imagine something? So there is as a mathematician, This is not a special thing. Any mathematician can think dx square, that coefficient is some function of x, y, and z. And dy square, some function, maybe g of x, y, z. And dz square, some function, maybe h of x, y, z. So there is no problem for thinking like this. Okay, so the question is, what will happen if the coefficient of dx square is some function of x, y, z? This some function of x, y, z, and the coefficient of dz square is some function of x, y, z. Then what will be that? See, here you can see that this is a space which you consider our usual space, in which, so you represent by an x coordinate, a y coordinate, and an z coordinate, x, y, z. And there are, you can draw parallel lines to the axis of coordinates, and that way you can measure the distance. But when this coefficient become functions, your space will not be having this kind of nature, x coordinate, y coordinate, z coordinate, but rather your coordinate system itself will not be rectangular. They may be curves. Okay, so that is what is happening. So a mathematician, Riemann, it is called Riemann, he thought of generalizing the Euclidean kind of method, Euclidean concept. Okay, by incorporating the coefficients of this dx square, dy square, etc. Rather than taking that kind of metrics, he has taken a very general kind of metric. Okay, so that is what little introduction to the Riemann space I will tell. Okay, so next is the Riemann space. We are not studying any rigorous study of this, but I will make you understand how this Euclidean space and Riemannian space are different in nature. Okay, so I write the distance between two adjacent points, two adjacent, neighboring adjacent points, whose Cartesian coordinates okay, our usual coordinate system x, y, z perpendicular to each other, that is usually called Cartesian coordinates, because it was discovered by a mathematician called Descartes. That is why it is called Cartesian coordinates, are x, y, z, and x plus dx, y plus dy, z plus dz is given by ds square equal to dx square plus dy square plus dz square. Okay, so this distance, this is usually called the distance formula, and this is also has got a name, what is called the metric. Okay, now Riemann extended the concept, concept of distance to a space of n dimensions, and defined the distance define the distance ds between two adjacent points Let me write it in a more general way. Xi and xi plus dxi. You know, I from 1, 2, etc. up to n. This is our notation. Okay. x1, x2, etc. xn. The superscripts, they are the labels, not the powers. So x1, x2, etc. xn. This is x1 plus dx1, comma, x2 plus dx2 plus etc. Okay, so this is one point, this is another point. By the relation, so he has made it more general and write ds square is equal to, how you write dx1 square. That's a usual dx1, but its coefficient he has written is some g11. So this is a function of the coordinates. Okay, plus g22 dx2 square plus etc. jnn dxn square. And not only that, I have g12 into dx1 into dx2. These cross terms are also permitted. Plus g23 dx3 dx2 dx3. Likewise it will go. Okay, call this by 1. The coefficients this is plus. The coefficients GIJs, this is apostrophe, GIJs are functions of the coordinates. Functions of the coordinates. Xi. Functions of the coordinates xi. Okay, so this is something which is a more general kind of metric. Now, if you want to come to the Euclidean metric, what is the main difference? It is G12 should be 0, G23 should be 0, G11 should be 1, G22 should be 1, Gnn should be 1. Then you will get dx1 square plus dx2 square plus dxn square. Then that is the Euclidean metric. And the coefficients are 1. Okay, so that's the difference. The quadratic form 1. Quadratic form 1. Why it is called quadratic form? You can see that how this is dx1 square, dx2 square, dx1, dx2, its power 1, its power be 1. So 1 and 1, 2. Okay, so this such expressions are called quadratic form. 1 is called Riemann metric. Riemann metric. I will give you examples, then you will understand it properly. Metric. And any space. In which the distance is given by such a metric. Such a metric is called Riemann space. Riemannian space. Okay, so what is it's an n-dimensional space in which the distance between 2 points is given by this. Okay, the distance between 2 points is calculated by this. Then we call this as the Riemann space, Riemannian space. Okay. Now, suppose I want a particular case of that. From this, I can derive the Euclidean space. Okay. So, let me take a particular case. In particular, you take a coordinate system. In particular, if we take a coordinate system, xi, which takes the form, if you take a coordinate system xi in which the metric takes the form, in which the metric takes the form ds square is equal to g11 dx1 square plus g22 dx2 square plus etc. plus gnn dxn square. Okay, so no other terms, only this. You see g1 dx1 square, dx2 square, dxn square. Okay, and where g11 equal to g22 equal to etc. gnn equal to 1. That is ds square equal to dx1 square plus dx2 square plus etc. dxn square. Call this by 2. Okay, then metric 2 is called Euclidean metric. And the corresponding space is called Euclidean space. Okay, so Euclidean space is the one with the metric, the distance between 2 points defined like this. Okay, now let me see what is a metric tensor. This is our topic. What is the meaning of a metric tensor? Metric tensor. This is also called fundamental tensor. This is playing a very important role. Okay, so the distance between 2 points in an n-dimensional in an n-dimensional space is assumed to be a constant. Okay, so that means if you take any 2 points in space and you calculate the distance between them, then that will be same. That's a fixed one. If you measure it from any other coordinate system, in a space you can have different coordinate system. Okay, you should understand the situation. Suppose you take our two-dimensional, you can call it as a two-dimensional space. I can use Cartesian coordinate system, x and y. I can as well use polar coordinate system, but the dimension is 2. And I consider 2 points, and the distance between them I can measure it by using Cartesian coordinates, and I can as well find out the distance between them by using polar coordinates. Then the distance will be same. Distance is not going to change. So it is a constant. Okay, any coordinate system, you measure the distance between 2 points, that will be always a constant. Therefore, you can say that all the constant means it is invariant. Any quantity which is invariant under coordinate transformation is a tensor, and that tensor is of rank 0. That you know. A tensor of rank 1 is a vector, a tensor of rank 2 matrix, a tensor of rank 0 is an invariant quantity, that is a constant. Okay, this one should you already know. Not one should know, you already know. Okay, the distance is considered to be a constant, and hence it is independent of, and hence it is independent of coordinate system. Coordinate system. Okay, so constants are constants. You can call it as invariants. Invariants are tensor quantities. Of rank 0. Of rank 0. Okay. Now, you know, when I express this equation 1, let me go back to that metric 1. Okay, this metric I can express like this. This is equal to Gij dxi dxj. Okay, dxi dxj. Okay, I can even call this as 1. Both are ऊपर का और this one, both are 1. इधर भी आप इक्वेशन के नीचे ये भी ऐड करो, Gij dxi dxj. Now what does it mean? This is something I and j both are dummy. Okay, when both I and j 1, what I will get? I will get this. Both I and j 1, I will get this. G11 dx1 that is dx1 square. Both I and j 2, then I will get this, because it is a summation up to n. I and j both n, I will get this. Now I can have I equal to 1 and j equal to 2, then I will get this. I equal to 2 and j equal to 3, I will get this, except all the quantities will get from. This is Einstein summation convention. Okay, so Gij dxi dxj. I can write in short like this. Okay. So now, let me come back to this. Okay, so quantity is a tensor of rank 0, any constant. Now dxi is a displacement vector. Is a displacement vector. Okay, and hence it is a contravariant vector, displacement vector, and hence it is a contravariant vector. Why it is a contravariant vector? Because you know, suppose you make a transformation from one coordinate system to another coordinate system. See, x bar I is x bar I of x1, x2, etc. xn. आप इसका ट्रांसफॉर्मेशन कैसे लेंगे? What is dx bar I? Dx bar I is equal to del x bar I upon del x1 dx1 plus del x bar I by del x2 dx2 plus etc. del x bar I upon del xn dxn. ये इंस्टेंट समेशन कन्वेंशन क्या है इसका? dx bar I is equal to del x bar I by del x k dxk. Okay, using Einstein summation convention, I can put it like this. अभी ये quantity आप देखो. Suppose I call it as this quantity as something tk, ti, t bar I, and this is ti, right side ti, tk. Then this will be del x bar I by del xk. So आप ये transformation law देखो. A transformation law says that this quantity is a contravariant vector. So that's why I'm saying it will transform like a contravariant vector. So the reason for this is this. So that is why displacement vector is a contravariant vector. Okay? I think that there is no doubt in it. Hence their outer product. Hence their hence the outer product of, let me explain more. Hence the outer product of dxi and dxj is a contravariant tensor of rank 2. You agree with me or not? Nobody is speaking anything. dxi, this is a contravariant vector. dxj is also a contravariant vector. They are outer product, the product of these two. Okay, so what is that? This is a vector, this is a vector. Their outer product is a contravariant tensor of rank 2. You did a lot of problems for proving this. It is not a new thing. Okay, because iska rank 1, so when you take the outer product, it's rank 2. Okay, so you may make two equations, two transformation laws, then you combine it, then you can see that it will be a contravariant vector. Okay. Hence, so now what you can say? So now I just want to know this thing. See, everything you can understand by using the things which you already studied. See, let us take this. What is my equation 1 kya hai? ds square is equal to gij dxi dxj. Okay. And now I want to know what is the nature of this gij. It's a doubtful quantity. Gij is coming, g11, g12, etc. is coming as the coefficient of dxi, dxj. And I don't know whether it is a tensor or not. So this is a doubtful quantity. But I know this displacement vector is a tensor. This is also a tensor. This is contravariant tensor. This is covariant tensor. When I multiply these two on the left side, you see, it is a distance. Distance is a number. So this is a tensor. This is a tensor of rank 0. Okay. So when I multiply this one with another quantity, I am getting a tensor in which I know this is a tensor. This is a tensor. So by quotient rule, I should say that this also should be a tensor. Okay, so if these two represent a contravariant tensor of rank 2, this should be a covariant tensor of rank 2 by quotient rule. Okay, so this is this is a use of important use of the quotient theorem here. Okay, so now I say that we have ds square is equal to gij dxi dxj. Okay. We want to find the nature of the quantity, gij. Okay, for that we can use quotient theorem. Quotient theorem or quotient rule. Okay. The LHS is a tensor of rank 0. dxi dxj is a tensor of is a contravariant tensor. Is a contravariant tensor of rank 2. Hence, gij should be by quotient theorem. Gij should be a tensor, a covariant tensor of rank 2. Okay, so do you follow me? Any doubt is there? You can ask me now.
Yes, sir.
Okay, so this is a mere direct use of the covariant, the quotient rule. Okay, so we have come to this one. Now I just have this result. So next, let me take it as a problem or whatever it may be. Problem. Show that gij is a symmetric tensor. Okay, solution. This gij, one good property is that it is a symmetric tensor. Okay, solution. How can you prove that it's a symmetric? You know, the second rank tensor is nothing but a matrix. Okay, and you know what is a symmetric matrix? So what is a symmetric tensor? A symmetric tensor means, okay, so how can you define symmetric tensor? Gij is called symmetric. Symmetric if Gij is equal to Gji for all I and j. Okay, so when I say Gij, it's a covariant tensor of rank 2, then you should mean this G11, G12, etc. G1n, first row, G21, G22, etc. G2n, second row, etc. Gn1, Gn2, etc. Gn. So it is nothing but this matrix. Okay, so when do you say that this matrix is symmetric? When you take the transpose, it should be equal. Gij should be equal to Gj for every j and I. Okay, then you call it as a symmetric. And also you know that this matrix, any matrix you take, you can write it as the sum of a symmetric and a skew symmetric matrix. This result also you have studied it. Okay, so this is we also know that Gij can be expressed in the form of a matrix. What is that? G11, G12, etc. G1n, G21, G22, etc. G2n, and Gn1, Gn2, etc. Gnn. So this matrix. Further, Gij can be expressed in the form Gij is equal to Aij plus Bij. Okay, Aij, sum of two tensors where Aij is equal to half Gij plus Gji, and this is symmetric. This is okay. Okay.
Yes.
And Bij is equal to half Gij minus Gji. So this is skew symmetric. Okay, so you see this simple idea. Gij, see what is Aij? Aij is this, and what is Bij? Bij is this. अब ये दोनों ऐड करें तो क्या मिलेगा? माइनस Gji प्लस Gji कैंसिल हो जाएगा. इधर आपको हाफ Gij plus half Gij will be Gij. Okay, so Gij can be written as Ai plus B, Aij plus Bij. Now the first one is symmetric. Why the first one is symmetric? इसका ट्रांसपोज आप ले लो, ये Ji करो, ये Ji, when you take Ji, this will become Gji, this will become Gij. That's the same as the same thing. Okay, and इधर Bji करे तो क्या मिलेगा आपको? When you write Bji here, this will become Ji, this will become Ij. Okay, so that what happens? you can, it will be nothing but the negative of this. So from this you can see that Bij is minus Bj. So that's why it is called a skew symmetric. Okay, but the sum, so any, this is the result, any matrix, n by n matrix can be written as the sum of a symmetric matrix and a skew symmetric matrix. So that symmetric matrix is this, sum divided by 2, and skew symmetric matrix will be this one. Okay, so it is possible for you to write down like this. Now, aqua ds square is equal to, what is ds square? Gij dxi dxj. Okay, now what is Gij? Gij I have written as Aij plus Bij. Okay, Aij plus Bij. Gij. Then this into dxi dxj. Okay, now I consider this one, this part. Okay, take this dxi aij to this left side. So I have gij minus aij, that into dxi dxj, that is equal to, what is on the right side? Bij dxi dx. Okay. Now can you tell me what will be this right hand side? Okay, if I take now call this by 1. Now I am looking for the right side, Bij dxi dxj. This is equal to, you can interchange I and j, because I is dummy and j is, I ke jagah I can put j ke jagah I, there is no change in that. So Bji dxi dxj dxi, I can put it in this way, because what I did is that I and j I interchange. I can do it because it is a dummy. Dummy can be replaced by enemy. But what is this Bji? It is minus Bij. Why? Because B is a skew symmetric one. Okay, and a dxi I write first, because they are differentials. I can interchange that. This is the reason, because Bij is skew symmetric. Skew symmetric. So now take to the one side. So this will become Bij 2 times Bij dxi dxj equal to 0. And you know dxi dxj, they are coordinate differentials. They are arbitrary. They cannot be 0. Okay. So which implies that Bij equal to 0. This implies that Bij equal to 0. Okay. So if Bij equal to 0, in this case, what will happen? From 1 we get Bij idhar 0 kare to I will get this. Sorry. The total Bij, this right hand side equal to 0. I need not write these steps. So this 2 times this one, Bij dxi dxj equal to 0. This is what I am getting. 2 cannot be 0, therefore this will be equal to 0. This is equal to 0 means right hand side is equal to 0. Okay, so therefore RHS of 1 is 0. Okay, RHS of 1 equal to. So what does it mean? That is Gij minus Aij into dxi, dxj equal to 0. So these are coordinate differentials. They cannot be 0. So this means that gij minus aij equal to 0. So which means gij is equal to aij. Okay, but what is aij? What is aij? It is symmetric. It is, we defined it like this. This is symmetric. Therefore, gij is symmetric. Since aij is symmetric, aij is symmetric, we have gij is symmetric. Is symmetric. Okay, so we proved that this is a symmetric tensor. Gij is a symmetric tensor. Okay. Now there is another term what is called conjugate tensor. Conjugate tensor. So this is also an important one. So what do you mean by a conjugate tensor? Let G be the determinant, be the determinant of gij. आपका मैट्रिक्स मिला ना gij मैट्रिक्स, वो मैट्रिक्स का डिटर्मिनेंट यू टेक. ओके, and gij, and there is a capital Gij, denote the cofactor of Gij in G. Okay, so look to the notations. Gij means, so I just write down Gij. इसका मतलब क्या है? Gij means G11 etc. G1n, G22 etc. Gn1 etc. Gnn. So this matrix is called Gij. What is G? G means determinant of G11 etc. G1n etc. Gn1 etc. Gnn. So this is called G. Okay, now what is Gij? Gij, it is a cofactor. You know what is cofactor? What is cofactor?
Yes.
Gij. Row and column you remove it. Okay. Gij, suppose Gij is coming somewhere here. That row and column you remove it, then you find the determinant. See, for example, G11 is equal to minus 1 raised to 1 plus 1 into determinant. This first row and first column remove करो, बाकी सब. Okay, so कौन सा आएगा? G22 22 etc. G2n etc. Gn2 etc. Gnn. So this is usually called the cofactor matrix. So that sense you should understand. So Gij is the cofactor of Gij in G. Okay, we define G upper ij by the relation Gij is equal to capital Gij divided by G. Okay, so this is the way I am defining. So G upper ij means cofactor divided by determinant. Okay, since Gij is symmetric, Gij is also symmetric, and therefore G upper ij is also symmetric. Okay, if G lower ij is symmetric, then upper ij also will be, because this is merely a number and a denominator. So that is merely a number. What's the time? Okay, 5 minutes. Okay, so this way I am defining the upper ij's. Okay, so G upper ij is also symmetric. Now you look to this one, Gij into Gij. You take the product. Okay, so what is this? Gij, this one. G upper ij I replaced by this one, Gij divided by G. Okay, now can you tell me what is this Gij into Gij? This Gij into capital Gij? It is nothing but the
Scalar.
Oh, so what is that scalar?
Rank is 0 to 10.
And rank 0, that is true, but can you tell me what is exactly that scalar? Scalar का value क्या होगा पता है?
1.
It is G. It is the determinant.
Oh.
It is the determinant. So determinant you can find out in terms of cofactor up matrix theory एक बार revise करो. Okay, Gij multiplied by this one, so it is nothing but G, the determinant. So I will get G upon G. I will get this will become 1. Okay, so Gij, its value is 1. And suppose I take Gij, Gkj. So this will become